For the remainder of the videos, we're going to work on objective number 2, find the complex zeros of polynomial functions. Just very briefly, complex zeros and complex number system. I grabbed a Venn diagram to try to show you the relationship between our complex numbers that we've looked at before. But if you look at our entire complex number system, every number that we can possibly conceive, things that we've studied before, whether the natural, integers, rational, real algebraic, or just real number system, they're all inside the complex number system. So in essence, when they ask us to find the complex zeros of a polynomial function, they're asking us to find all the zeros. And now we're going to have to work with these complex numbers and find those solutions as well. So we're going to be working with finding every possible solution of a polynomial function. When we have a real one, just to kind of enlarge this one more time, when we have a real zero of the polynomial function, every real zero will be shown on your graph. It'll show up as a x-intercept, or where it crosses the x-axis. The complex solutions are going to be the ones that we will not see crossing the x-axis. So when we look at our graph, we're going to be able to tell how many real solutions there are, and then that'll also tell us how many complex solutions are available. One of the key ideas to this is the fundamental theorem of algebra. Fundamental theorem of algebra basically tells you, based on the degree of the polynomial, you'll know exactly how many complex solutions there are. And keep in mind, this complex number system is the entire set of numbers that we could possibly find answers to. They will include our real number system as well. So first of all, our fundamental theorem of algebra tells us exactly how many solutions we should find. Secondly, they give a linear factorization theorem, and the linear factorization theorem really ties into this idea of the fundamental theorem of algebra. For instance, if we have a 6-degree polynomial, then by the fundamental theorem of algebra, we should be able to find 6 complex solutions to this polynomial. That means we should be able to write out 6 linear factors of that same polynomial. So we're going to take off on this idea, and we're going to be writing, first of all, the polynomial function that has the given set of zeros. So one of the important things to remember is, according to the conjugate root theorem, and I don't remember where we've stated that or where this is introduced, but the conjugate root theorem basically says if a plus bi is a 0, then a minus bi must be a 0. They will always come in pairs. A very simple example of that is when we have x squared minus 8. Plus 8 equals 0. If that happens to be one of our factors that we have in our polynomial, well, we try to solve that by saying x squared would equal a negative 8, and x would equal plus or minus the square root of a negative 8. These conjugate factors means that they will always come in a pair of complex numbers, a plus and a minus. So this will be a plus and minus. We're going to take the square root of a negative 1 out and represent it as an I. We're going to take the square root of 8 and we're going to reduce it down to, that's 4 times 2, or 2 times the square root of 2, I. But this is what they're saying is a complex factor. A complex factor never comes alone. It always comes in a pair, a plus and a minus. That's what the conjugate root theorem is saying. If a plus bi is a root, then a minus bi is also a root of the theorem, or of the polynomial. So here's our first set of examples. They asked us to create a polynomial function. We're going to write a polynomial function that of least degree with the real coefficients in standard form with the given zeros. So they're going to tell us what the zeros are. They tell us a negative 3, a positive 1, but that has a multiplicity of 2, so we got to count that twice. And it has 1 complex root. So as soon as they tell me I got 4i in there, by that complex root theorem, I also know that there's a negative 4i. So really, they kind of give it to you in little bits and pieces, but this is in plus and minus for I. They want you to know that if they give you 1, there's automatically a second. So what we have is x minus 3 is a 0, which means its related factor is x plus 3. We always take the opposite of the 0. If 1 is a 0, then we write down for a factor x minus 1. Now they also told us it had a multiplicity of 2, which means we're going to put a power of 2 on x minus 1. The next part of this is working with these complex roots, which means we want to take the opposite of our root, which means if it's 4i, we go x minus 4i, if it was a positive 4i, and then if we do the, if it was a positive 4i, then it would be x minus 4i. If it's a negative 4i, then it's x plus 4i. So really what we've generated is a polynomial that has 1, 2, 3, 4, 5. This is going to be at least a fifth degree polynomial. We want to write it as f at x. And I didn't leave myself enough room, so I'm going to have to rewrite it. The only other thing that we have to worry about is the vertical stretch or shrinks. And here's what they do with it. F at x equals, we've been using a to represent a vertical stretch or shrink of, the rest of this is all the factors that we've created. X plus 3 times x minus 1 squared times x minus 4i times x plus 4i. Now we have kind of the unfavorable task of multiplying these all together to get the polynomial. Now because a can be any real number that we want, it has an infinite number of solutions, or there's an infinite number of equations that we could create. So to keep it relatively simple, we normally just let a equal 1. It's kind of like a baseline. It's a family that we're going to create of these factors. So don't really worry about a. I just want to introduce that there is an infinite number of solutions that we could have, but of those infinite sets, we're just going to use where our value of a is equal to 1. Don't worry about your vertical stretch and shrinking. So because a is 1, I'm going to kind of forget about it for a little bit, and now we've got this task of multiplying all these numbers together. So I'm going to attack that x minus 1 squared first. So I'm going to leave the x plus 3 here. The x minus 1 squared to give me an x squared minus 2x plus 1. And then I'm going to attack these two next. We can multiply in any order that we want. And I'm going to end up taking our squared first. Now I'm going to multiply these conjugate factors. So x times x is x squared. We got a positive 4xi, we have a negative 4xi. The outside, inside, they cancel. So then all we're left with is a negative 16i squared. Okay, one of the things we need to remember from unit 0 is I squared is equivalent to a negative 1. So we're going to replace I squared with a negative 1. If this is a negative 1 times a negative 16, it becomes plus 16. So I'll have an equivalent expression that says x plus 3 times the quantity x squared minus 2x plus 1 times x squared, and this will turn into plus 16, parentheses. Now we still have to multiply all these together, so it becomes quite a bit of distributing in this. I'm going to choose to multiply these two together. I like multiplying those binomials together first and then working with the trinomials. So I'm going to take an x times x squared, which is an x cubed. I'm going to take an x times 16, which is 16x. I'm going to take a 3 times x squared, which is 3x squared. I'm going to take a 3 times 16, which is 48. I have to take that answer times x squared minus 2x plus 1. So rewriting this, I'd rather have it in standard form, x cubed plus 3x squared plus 16x plus 48. You have to multiply that times x squared minus 2x plus 1. So now it's a matter of distributing all of these through. So I'm going to choose to distribute my trinomial to this larger polynomial. So I'm going to take the x squared times x cubed, and that is x to the 5th. I'm going to take the x squared times 3x squared. That's going to be a positive 3x to the 4th. Take the x squared times the 16x, and that's going to be plus 16x to the 3rd. The x squared times the 48, which is going to be plus 48x squared. Next time through, I have to distribute the negative 2x. So now I'm going to take the negative 2x times all of these in my first polynomial. So negative 2x times x cubed is a negative 2x to the 4th. I'm going to put it right underneath the other one so I can collect like terms a little bit easier when they get this long. I find it easier to put them in columns rather than keep running like terms across the page horizontally. So now I'm going to take the negative 2x times 3x squared. That's going to be a negative 6x to the 3rd. I'm going to take the negative 2x times 16x. That's going to be a negative. 2 times 16 is 32. X times x is x squared. And I got a negative 2x times 48. That's going to be a negative. And that is a 96x. And there weren't any other x's, so I put it on the end. Now the final number I have to distribute is the positive 1. So multiplying by positive 1 doesn't change our values at all, but I just got to make sure I take the 1 times x cubed, which is x cubed, put underneath my other x cubes. Got 1 times 3x squared, which is plus 3x squared. And I got a positive 1 plus 16, so that's going to be, or plus 16x, so plus 16x. And a positive 1 plus 48, or times 48, which is 48. Okay, so now I've organized my like terms underneath each other, so the final answer to this thing is going to be a polynomial that is x to the fifth. We have 3x to the fourth minus 2x to the fourth, so plus x to the fourth. We have 16x cubed minus 6x cubed, which is 10x cubed, plus another x cubed is 11x cubed. And then we want to collect these like terms. 48 minus 32 should give us 16. 16 plus 3 is 19, so it's 19x squared. And 96 minus 16 should give us a negative 80x plus 48. Now what we've created is a polynomial of fifth degree. As we said earlier, we could bring this value of a back in here, and we could say a could be any real number, which gives us an infinite number of polynomial functions which would have these zeros that they gave us at the very beginning, which I'm having a hard time, but these were our zeros, negative 3, 1 with multiplicity of 2, and 4i, which means we automatically have plus or minus 4i. It's a lot of distributing, but this is what they're after. They're after this polynomial function that is, or that has those zeros. So that's the first example of that. We're going to come back, we're going to look at a second example. You're going to get lots of practice of distributing on this. So this time we have, from the very beginning, 1, 2, it looks like 3, but if 1 plus I is a factor, or a root, then 1 minus I has to be the other one. Remember, your conjugate root theorem says they will always come in pairs. So those two are going to get paired up. And these other two are two irrationals that kind of got paired up as well. So if 2 times the square root of 3 is a 0, then its related factor is x minus 2 times the square root of 3. If negative square root of 2 times square root of 3 is a root, then x plus 2 times the square root of 3 is its related factor. Now here's where we got to be a little bit careful on these, because we've got 1 plus I. So it's always the opposite of your root. So it's the opposite of 1 plus I that we put in front, put the x in front. So it's x minus the quantity 1 plus I times, and our other associated, if this is the root, then our other associated factor is x minus, now you take the opposite of 1 minus I. So we got to multiply all these together to figure out what polynomial has those zeros. I'm going to clean up these first, and then we'll worry about the other multiplication. So x minus 2 times the square root of 3 times x plus 2 times the square root of 3. Then we got times. Now we're going to simplify this. It's going to be x minus, I'm distributing the negative, so minus 1 minus I times, it's going to be x minus 1 plus I. Now I have my 4 factors that we need. I'm going to take and start multiplying these two binomials together. They're conjugates, so their outside inside should cancel, so we're going to have x squared. The outside and inside will cancel. We're going to have a negative times positive, which is negative. 2 times 2 is 4. And then the square root of 3 times the square root of 3 is 3, so it's really 4 times 3, which is 12. So those just give me x squared minus 12. We have a little bit more work to do with these because it's a trinomial times another trinomial, so we're going to have quite a bit of distribution in here once again. So I'm going to take this x times x, which is x squared. I'm going to take this x times negative 1, which is negative x. I'm going to take this x times I, which is plus xi. Then we're going to multiply through by negative 1. Negative 1 times x is a negative x. Negative 1 times negative 1 is a positive 1, so I don't have any of those, so I'll go plus 1 out here. A negative 1 times I is a negative I. So negative I. I don't have any just i's either, so that's what that one's like. Now I got to multiply through by negative I. So negative I times x is a negative xi. So that's going to be a negative xi. Like term is here. A negative I times a negative 1 is a positive I, so plus I. Negative I times a positive I is a negative I squared. So I still have this factor of x squared minus 12 that I need. And now I've got to collect all the like terms that I got from here. So what we have is x squared minus 2x. These will reduce to 0. These will reduce to 0. Remember that I squared is equal to a negative 1. So this is really minus a negative 1. Minus negative 1 is plus 1. And plus 1 is plus 2. So all of the i's, or the imaginary complex solutions or ideas, drop out of our factors. And now we still have to multiply through by our x squared minus 12. So x squared times x squared is x to the 4th. X squared times negative 2x is negative 2x cubed. And x squared times 2 is plus 2x squared. Next row, I'm going to multiply through by the negative 12. Negative 12 times x squared is a negative 12x squared. You can align it with its like term. Negative 12 times negative 2x is a positive 24x. And negative 12 plus 2 is a positive 24. Now we're going to collect our like terms, and that'll be our polynomial. At least one of the possibilities of the polynomial. So x to the 4th minus 2x cubed, then minus 10x squared, plus 24x, plus 24. This is our function rule. If we want to indicate it can be any one of an infinite number of solutions, we can put an a out front. If we leave a as 1, then that was our solution. But this represents all of the possibilities for this function rule. So it's a 4-3 polynomial. As you can see by the fundamental theorem of algebra, it has 4 roots that are complex, 1, 2, 3, 4. So it's a 4-3 polynomial as expected.